Uh, so let's get started. Today's going to be pretty short, apparently. I overestimated how much time this page is going to take. Uh, this page with like problems 7, 8, and 9. So the way that these sets of problems work is we are considering the same graph, but for each of the individual problems, we're sort of interpreting the graph differently. So for 7, we view this as a graph of the function v of x. Then for number 8, we're going to view it as the derivative of v, and then for 9 as a second derivative. So each time we're going to have to reconsider what it means for that graph, like what the notions of increasing and decreasing, min and max, concave up, concave down, inflection, what all those different terms mean when we view this as a first derivative or second derivative or just the original function v. So there'll be a little bit of context switching involved with that. And yeah, but yeah, let's go ahead and do that. So firstly, we are considering this as just the function v of x, and we're thinking about when does it increase or decrease. So for this, you can really just read it off of the graph, since the idea of increasing, decreasing is very intuitive, or just straight up read it. But in terms of derivative, we should also maybe think about derivative. Increasing means that the derivative is positive, and decreasing means that the derivative is negative. But so for here, I would say minus infinity to 1, and for decreasing from 1 to infinity. Okay, now for local max, well, we see a local max at x equals 1, and local min, well, there aren't any, since this function is going, we're kind of imagining that the two ends of it are going down to minus infinity. Concave up, for that, that's nowhere, none, I guess. And concave down, that's everywhere, minus infinity to infinity. It's concave down everywhere, as you can tell. Inflection points, there are none for this. So by definition, an inflection point is a place where the concavity changes. Since the concavity is always downwards, there's no point of inflection. Okay. All right. Now for number 8, we need to reinterpret this. So now instead of this being the function v, we think this as the derivative. This is v prime. Okay. Then increasing and decreasing. Now we do need to go back to the definition. So increasing means that the derivative is positive, but this is now the derivative graph. So it's increasing when the values that you get out of this function are positive, meaning that it's increasing from -1 to 3, and as decreasing everywhere else, where the function is negative. Okay, so increasing from -1 to 3, and decreasing from minus infinity to -1, union 3 to infinity. For part B, the information about min or max, well, first of all, these local mins and maxes happen when the derivative is equal to 0, right? So that means that they occur at either this -1 or at 3. And to tell which it is, it's all about, like, is it going from plus to minus, or is it going from minus to plus? So this guy, minus to plus, decreasing to increasing, this is a local min. Okay, so we can jot that down. Where's my cursor? X is -1 as a local min, and conversely, x is 3 will be a local max, going from increasing to decreasing, plus to minus. Okay. Right. Now for C, concave up versus down. So concavity is the second derivative, right? But we're viewing this graph now as the graph of the first derivative. So to determine concavity, we need to take another derivative on top of it. Okay, and so for being concave up, that's when the derivative of this graph is positive. Well, it's positive up until 1, from minus infinity to 1. So that's going to be when the thing is concave up, minus infinity to 1, and concave down will be from 1 to infinity, right? All we're doing is we're just taking yet another derivative on top of this graph, and we're just checking when is it positive, when is it negative. Inflection point, Well, that's when the second derivative is equal to 0. So that's going to happen right there at x equals 1. Technically, there's a bit more to that, to the definition of inflection point. Not only is the second derivative supposed to equal 0, but the concavity around it is supposed to change. But here it does, so we have no problems with that. Concavity is supposed to change. Yeah. Okay. All right. Now for number 9, we reinterpret the graph yet again. So now we think of this as depicting the second derivative. Okay, so concave up and concave down. For a second derivative, that's just, is it positive or is it negative? So that tells us that concave up is going to be when this graph is positive. That's from -1 to 3. And concave down is everywhere else. And then for inflection points, again, concavity needs to change. And we do see that it does actually change. Over here, the concavity, the second derivative, viewing the graph as the second derivative, this is negative to positive, positive to negative. So both -1 and 3 are going to be inflection points. So x is equal to -1 and 3. Both work. Okay. Any questions on this page? Not seeing any questions. All right. So last we have number 10. So number 10 is basically it's a single problem that falls into the category of being what we call curve sketching. So the idea is that for curve sketching, we're given a function and we want to gather as much data as possible on that function in order to graph it or sketch it. And the kind of information that we would typically gather. So first of all, typically it's not going to be a polynomial. Polynomial is a little bit too easy. But instead, usually we would give you something like a rational function. And so on a test, this kind of problem shows up very frequently on tests. We would give you a rational function and we would give you the derivative and the second derivative of that function. Like we would tell you what the derivative and second derivative end up actually being. And then you're supposed to read the information off of those all that information. The reason we give you the first and second derivative is because it's just to save time. Otherwise, you have to go through a somewhat tedious process of doing quotient rule. Right, but so then what is all the information that you would normally gather? You would gather asymptotes, intercepts, so x and y intercepts, asymptotes, then the information from the first derivative, which would be the increasing, decreasing, local min, local max, and then from the second derivative, you'd get the concavity, you'd get the inflection points. So that would be basically all the information that you can gather from the function. And then you just take all that information together and try to sketch the graph using all of it, which is what we're going to do in part F. Right, so let's go ahead and run through this process. So, right, first of all, critical numbers. So we need to take the derivative and set equal to 0 and solve. So for this function, I would prefer to expand it out because that'll make taking the derivative easier. So this is going to be 3x squared minus 12x, which we would set equal to 0. And so then we factor, we'll get at x minus 4 equals 0. Therefore, we get the critical numbers x equals 0 and 4. Okay. For increasing and decreasing, what we need to do is sketch a number line, do the sign chart for the first derivative. And the factored form like this tells me that it's going to alternate since yeah, both x and x minus 4 are raised to the first power, so it's going to flip in sign when you jump over the 4 and when you jump over the 0. Okay, then we can just write it down. Increasing happens from minus infinity to 0 and from 4 to infinity. Decreasing happens from 0 to 4. Okay, next we want to determine concavity. Well, that's going to require that we have the second derivative. So we need to compute the second derivative. Well, I'm going to use this version of the first derivative, and I'll just calculate it from there. So I'll get a 6x minus 12, set it equal to 0, and solve. So 6 times x minus 2. So then x is equal to 2. And the reason that I'm solving for x equals 0 is so that I get my divider for the sign chart of w double prime. Okay, from here I can then pretty quickly see this, right? These are the signs. And so that's going to tell me concave up and concave down. And I'll use this abbreviation, concave up, concave down. Typically I don't use that, but I don't know, maybe I'll get used to it eventually. Yeah. Okay. And inflection points. Well, inflection points would be when the second derivative is equal to 0, which we found at x equals 2, and also when we would have to check that the concavity changes from one side to the other, and it does. So great. So we found x equals 2 using inflection point. And then local min and max. Well, this we can read from the first derivative sign chart. Plus to minus, let's see, local min, local max. So yeah, plus to minus is a max. So x equals 0 and x equals 4 is a local min. Okay. Now, in order to sketch these things, I really want coordinates for the local min and max and for the inflection point. Like those are nice points to put on my chart before I sketch the whole thing out. So we're gonna need to plug into W. All right, so let's see. First, let's try to plug in 2. So what is W of 2? Well, that's going to be 4 times -4. So we get -16. So we have the point 2 comma -16. Okay, so 2 -16 is the inflection point. For W of 0, I think you can just calculate that right away. That's just 0. Okay. 0 comma 0. But then for 4, 16 times -2. So I'm going to get -32. Okay, so we've got all the points. And there's a final comment here where it says that 6 is also a root. So you can just read off that from this function, this factored form. Right? And so that also contributes another point that we can graph on this thing. Okay, so now 1, 2, 3, 4, 5, 6. Maybe I'll put another one. 6 there, 3. And what I'm going to need to do is put -32 somewhere. And let's put -16 halfway. Oops, that's a little bit too spread out. -16. Right, so 0, 0 is a point on the graph, and 0, 6 is a point on the graph as well. Those are the roots of this polynomial. Then we've also got 4 comma -32, which is about there. And we've got 2 comma -16, which is about there. So then, well, 0, 0 is supposed to be a local max, which means that around it, it kind of looks like this. 4 comma -32 is a min, so it's going to curve upwards afterwards. And this 2 comma -16, this point here, is supposed to be an inflection point. So we kind of just need to shape things, connect the dots in such a way that makes that a point of inflection. And also, I can help to keep in mind that this thing is supposed to look cubic. And so you can basically see from there like what this is supposed to look like. looks something like that. Yeah. And so there you go. That's the rough sketch of this. Okay. Any questions? If there aren't any questions, then I guess we can end here.